Okay, just to disclose as well as acknowledge the funding sources and where the resources come from for all of these projects that I'm going to tell you about. A lot of this came from the USDA PRRS Cap 1, National Pork Board, Minnesota Pork Board, Rapid Agricultural Response Fund, the BI PRRS Research Initiative played a big role, Genetipork, and then our SDEC partners, which are companies and practices you see there that provide us with funding as well as in-kind support for operation of our farm. So PIC, BI, Genetipork, Mike Strobel's group, Pharmaceutical Solutions, Pfizer, Novico, Novartis, Pipestone, Fairmont, Swine Vet, and Martin Bonneau's group in Quebec. So thank you very much. I'd like to frame the presentation based on 3 questions that we've been trying to answer the last few years. Number 1, is MERV-16 air filtration effective against multiple pathogens? We know it has a cost. Perhaps the cost is more justified if it can stop other things besides PRRS. Do cost-effective alternatives to MERV-16 filtration exist? Obviously, we want to see if we can do this cheaper. And then an interesting study that I just finished with Satoshi's help. Can airborne spread of pathogens occur over long distances? We'll see what we found there. Okay. Very briefly, I'll give you the summary of our ongoing 2-year study. We've just finished year 2 and we're starting year 3. This is at our Swine Disease Eradication Center research farm. It's a model of a swine production region. I think you're familiar with it. But basically last year, Andrea Pitkin's work for an entire year, she showed that an air-filtered facility on site could prevent PRRS virus introduction for an entire year. But a non-filtered facility right next door, 4 meters away, would continually and repeatedly be infected with PRRS via the airborne route. Satoshi's taken the project over. We've added Mycoplasma pneumoniae to the source population infection or co-infection, along with our PRRS virus 1A4. After 1 year, or the second year that he ran the project, still no transmission to our filtered facility, and evidence of both agents passing via the aerosol route into the non-filtered facility. So similar results as we saw in year 1. So this is what that site looks like. There's a 300-head continuous flow grow-finish population right about where I'm standing, 120 meters away from these 2 facilities. This is our filtered facility with the MERV-16, and here's our non-filtered facility with a cool cell pad. No treatment there, obviously. And our weather station capturing weather data during the time when airborne transmission events occur. So we've moved on from when John Paul was there to a little bit better facility design now. Okay. So it looks like that the MERV-16 filtration system, and this is being, I think, replicated and documented very well in the field by people like Darwin Reichs and Paul Yeski's group, Gordon Spronk's group. It seems to work against PRRS virus as well as other pathogens too. Okay, second question. Do cost-effective alternatives to MERV-16 air filtration exist? MERV-16 filtration is not cheap. There's issues with air restriction, and so can we do this for less money? So we just finished a project that was funded by the BI PRRS Research Initiative with the objective of evaluating alternative methods for reducing the risk of airborne spread of PRRS virus. The treatments we looked at were other mechanical filters, similar to the MERV-16, just running synergized through a cool cell model. This was an idea Bob Morrison had. You know, can we just run disinfectant through our cool cell, through our evaporative cooling system? Is that enough to contact incoming virus and kill it? That's a good idea. Let's check it. And then also a new concept from Novico in Quebec, looking at whether antimicrobial filters can help. These are filters where the fibers are impregnated with various chemicals designed to kill viral agents. So it's a contact killing issue. The outcome we measured was whether there'd still be virus in air after treatment. And I'll show you the diagram. We used a chamber model that we modified a bit from our previous publication. In the donor chamber, we released artificial aerosols of varying concentrations using the MLV vaccine. There was a 1-meter duct connecting the donor chamber where we placed the intervention set point to the recipient chamber. And as we're collecting air in that chamber, we've got 2 cyclonic collectors from Midwest Microtech capable of collecting 400 liters of air a minute. We had 5-minute collection periods. That was a replicate. And then the samples we tested by PCR, and if PCR positive, by swine bioassay. So what does it look like? Here's a donor chamber. We've got a cold mist fogger aerosolizing various concentrations of PRRS virus from 1 log per liter all the way up to 7 logs per liter. In the donor chamber, we've got our treatment here. This is where we can put different types of filters in place. There's a fan that pulls the air down the duct and into the recipient chamber where the cyclonic collectors are collecting 400 liters of air a minute, again for a 5-minute replicate. With the need, we needed a way to neutralize the effect of the chemicals on the sample. Obviously, if we collected a sample and it's going to be run by PCR the night or overnight, the next day, if there were chemicals in the disinfectant or chemicals in the antimicrobial that got into that test tube and they continued to act overnight, we may get a false negative result. So after a 5-minute period of time, as I mentioned, we added a neutralizing broth to each sample to stop the activity of the disinfectant or the antimicrobial chemicals after a 5-minute period of time to eliminate the risk for false negative results. This is Day and Engley neutralizing broth that's commercially available. It's a really neat product. So after 5 minutes, as I mentioned, the broth was added to the sample. And before we ran the study, we tested the broth's ability to affect the PCR reaction or have any negative influence on the viability of the virus, and there was none in either case. So the broth didn't affect the diagnostic assays. First thing we did was validate the model. I'm going to show you a number of charts which are set up the same way. First column is the concentration of virus in air that we released in the donor chamber. So you can see we have 10 to the 1 per liter all the way up to 10 to the 7 per liter, again, by using tenfold dilutions of the PRRS modified live virus vaccine. So in the absence of intervention, the virus moves very nicely down the duct and can be collected by the cyclonic collectors in the recipient chamber across all concentrations. And the virus was viable when those samples were inoculated into negative pigs. Negative control, saline only. You can see we didn't have mechanical issues with contamination during our collection. So the model appeared to be repeatable. So then we began to place the various treatments in the duct, collecting air samples over a 5-minute period per replicate again and see what we can learn. So here are the mechanical filters, 10 to the 7 down to 10 to the 1, similar as the validation. The first filter we tested was the one we were using in our facility at the research farm, the Camphil-Farr MERV 16. You can see it blocked the movement of virus in air down that duct in every case. We then compared a Camphil MERV 14, which is a less efficient filter. It moves more air, so we thought it may be not quite as good as the 16. There's not as much fiberglass in that filter. And you can see that there was a break point where virus was able to pass through that filter. However, when you look at the economics of ventilating or filtering a 3,000 cell farm with a MERV 14 versus a MERV 16, there's probably about a 35 to 40% reduction in cost because you can move more air, you need less filters, and so overall this may be a better filter for wide-scale application of filtration across areas. Okay. We also compared 3 other MERV 16, so to speak. One from the US, one from China, and one from Turkey. And you can see here that there were some differences between how these filters performed under this model versus the MERV 16 from the Camphil company. Now when I went and did some digging, I learned that you can buy different grades or qualities of fiberglass. You can build different quality of frames. And so there's a lot of variability in how these filters are put together. And that may be one explanation of why we saw some differences across these so-called MERV 16 filters. So I'm encouraged by these results because when on our research farm, as we're collecting air and quantifying virus in air, we're finding quantities of virus down along these levels down here. I think this is a very aggressive challenge, perhaps artificially aggressive, artificially high. and not very indicative of what may be in the real world. So we'll see. Okay, what about Bob's idea about just taking Synergize, 1 ounce per gallon, and running it through the cool cell as the water is misted on the cool cell, letting that disinfectant just kind of coat that cool cell pad. We put a cool cell pad in our chamber model and recirculated water with Synergize at a 0.8% concentration, or 1 ounce per gallon. You can see, same type of a chart, lots of PCR positives. That's not surprising. This isn't a filter. Virus gets through the cool cell pad. However, it's dead. Again, after a 5-minute collection period upon addition of the neutralizing broth. So the virus is killed within a 5-minute period of time, even though it does pass through the cool cell pad by the disinfectant. And if you take the disinfectant out and you just run it with water alone, as you can see, positive virus, but also viable virus. So you need the disinfectant in the equation. Last was the antimicrobial filters. These are, as I mentioned, sheets of polypropylene with chemicals impregnated in the fibers. And the Novico company sent me 3 different models, 20 layers, 15, and 10. And so we put them in place and tested them. And you can see what we saw. Very nice data. Prevention of viral movement across the filter. In the 10-layer filter, that's the one they're thinking about putting out on the market, there were a few positives by PCR. However, when tested by bioassay, those samples were negative. And again, a 5-minute collection period with the addition of the neutralizing broth, which targeted those chemicals. Okay? So I believe these are true negatives, not false negatives. So conclusions, at least from this laboratory-based study, I think there are alternative methods for cost-effectively reducing the risk of aerosol spread of PRRS virus. As of now, we have removed the MERV-16 filters from our filtered facility at our farm, put in MERV-14s, and there is a Novico constructed antimicrobial filter building on our site too. So for the final year, we're going to be able to run the non-filtered control side by side with the MERV-14, side by side with the antimicrobial, to see how these filters work under these conditions. And I think an interesting point was that filter quality varies from source to source. Not all MERV-16s are created equal, in other words. And so it's important to understand the quality control program for where you buy these things. They're not all the same, even though they all stamp as MERV-16. Last question. Can airborne spread of pathogens occur over long distances? In other words, well, if I'm 2 miles from my neighbor, do I need to put a filter system in? Let's find out. Just recently, Andrea showed that in our model, over 120 meters, the virus can move from the source population to the non-filtered facility by aerosols. That had been the longest report at that point, and that's soon to come out. But as we all know, there's a bit of speculation beyond that. And the 2-mile rule, or 3.3 kilometers, has been used maybe for judging risk or placing facilities. And it's a little bit of a holy grail. It's a question that everybody always asks at these presentations. How far can it go? So let's try to answer. So the objective was to provide evidence of PRRS virus and Mycoplasma pneumoniae in air samples collected at 1 mile or 2 miles from our source population. Our hypothesis was, based on lots of conversations with many of you, is that, yeah, this can happen if the conditions are right. Okay? So what do we do? The source of our 2 agents, of course, was our production region model source population. As I mentioned, Minnesota 184 infected, Ohio 232 infected, running now consecutively for a year with both agents. We set up sampling points of 1 mile and 2 miles, 1.7 and 3.3 kilometers from the source. And really, the decision we made in where to sample each day was based on wind direction. Because Andrea's work showed that that's probably the biggest risk factor for determining whether virus is going to be in the air or not. In other words, when the virus is moving from an infected source to a naive population, the odds are 6.4 times more likely to find virus in the air than if the wind's blowing in the opposite direction. Common sense. So we basically looked at the weather vane each morning before we set out. And that's where we decided we would go, out to the 1 mile point and the 2 mile point based on that wind direction. We also collected from the source population exhaust fan at the end of the sampling time, a bit of a positive control, just to see if the virus and the bacteria were indeed coming from the source. We kind of used a sampler on wheels approach. We took the cyclonic collector and plugged it into the battery, into an old pickup truck. And we would move that pickup truck to this particular point based on wind direction. And we would position the vehicle so the passenger window would face into the wind. And we roll down the driver's side window as a bit of an outlet. But here's our collector. The air comes up underneath here. It's washed with cell culture fluid with 3% fetal calf serum. And we take that sample of liquid and we can test it by PCR. So it's basically just sitting in this cab. And we're trying to create a chamber here to see if we can catch air and look for virus. Okay. The sampling period was from September 30th out to November 17th of this year. The time we sampled, we began at 5 in the morning, and we usually ran till about 9:30 in the morning. The sampling interval was 30 minutes, so the machine would run for 30 minutes. We'd stop it. We'd take a sample. That was one sample. Again, at 2 miles, and then we would take our samples at 2 miles and move into 1 mile, take our samples at 1 mile. Our sample size was 300 total samples, 150 at each distance based on our power calculation. And then the assays we used were qualitative and quantitative PCR for PRRS virus, sequencing, and swine bioassay in case we found anything that looked promising to see if the sample contained live virus. And then with the help of Simone Oliveira in her lab at Minnesota, she's developing some interesting sequencing technologies for mycoplasma. So that was some of the methods. We had a lot of controls. Before we kind of got into this, we just wanted to see if we released virus outside the truck, would the machine find it? And so we placed our fogger a meter outside of the truck, just like we would set it up. And we collected, tested different liters, or different concentrations per liter, again, as we did earlier, 1 times 10 to the 1 up to 1 times 10 to the 7th per liter. We had a negative control just to make sure we didn't have mechanical contamination, so saline only, released with the fogger outside of the truck. Each day before sampling, while the vehicle was in the garage, we took an air sample from the cab of the vehicle. So the windows were closed. We ran that machine basically as I was taking my shower and getting ready to do this. I'd run the machine for a half hour in the cab in the garage just to make sure there wasn't contamination still in that cab. And we also took swabs from the interior surfaces of the cab, the dash, paddles, etc. So that was done before we started. Between replicates, as we took our half-an-hour period and we took the sample out, we then cleaned the machine. We sanitized the collector and swabbed it to make sure there wasn't any residual virus. We wore gloves and changed them between replicates. After sampling, after we were done, the cab was sanitized, the windows closed, and stored in the garage at the farm overnight. We set up a map. Here's our infected source. And then again, 1 mile, 2 miles, in all 8 of the cardinal directions. So based on wind direction, we would park the car in the opposite direction. So if the wind's coming from the northwest, we're going to start down here at the southeast. We're going to take our 2 mile samples first. Then we're going to move in. We're going to take our 1 mile samples. And then at the very end, we're going to go to the exhaust fan at the source population and take the final sample. This is what the landscape looks like out at the research site. You can see the corn's down, but there's not a whole lot in between. Here's the farm. This is 1 mile north. And there's the farm right about there. This is 2 miles to the northeast. So it's a very desolate part of west central Minnesota. Okay, what did we learn? Well, we collected 306 samples over 50 days. Remember, our goal was to get 300. So we got 153 samples per distance, 1 mile and 2 mile. All the swabs and samples we collected from the cab on each sampling day prior to initiation were negative. All swabs of the collector taken between replicates were negative, again by PCR. Our positive controls, just releasing virus in artificial concentrations, artificial aerosols from the outside, 1 meter away. We could easily find it from 1 log all the way up to 7 logs. That's not that surprising from our duct work. The negative controls, saline only, were negative. And in the source population, we had quite a clinical presentation during the sampling time, about a 20% morbidity, a 5% mortality. Of the 50 samples we collected from the exhaust fan at the end of the sampling period, 16 were positive for PRRS virus with a mean concentration by PCR of 3.9 times 10 to the 5th TCID 50 per ml. So that's RNA, not live virus. But we have demonstrated live virus in the past. 18 of 50 samples from the exhaust were mycoplasma positive by PCR. Just to show you a snapshot of what was coming out of that source population. Here, for example, is when we started, September 30th down to October 11th. And here's what was coming out of that source population, exhaust air. You can see it was very easy to recover these agents being expelled from the source population. And here, by RT-PCR, are the concentrations of virus, PRRS virus, in those air samples. So there was plenty of virus and bacteria being circulated and expelled from our source. Of the 306 PRRS samples that we tested, we had 4 that were positive. Here are the dates in which the samples were found: October 5th, 6th, October 22nd, November 11th. The time in which the positive sample was collected, so 6:30 to 7, 6 to 6:30, 5:30 to 6, 7 to 7:30 a.m. The site, the distance where the positives were recovered, so 2 miles. There were 4 samples out at 2 miles or 3.3 kilometers that were PCR positive, that we were able to quantify, so from roughly 1 to 2 logs based on RT-PCR at TCID 50 per ml. All 4 of them contained live virus when injected into negative pigs. And when sequenced, they matched our virus within about 1% of heterology to our virus, our Minnesota 184. Just here's a dendrogram. It's a little hard to see, but very, very nice clustered sequences, and within roughly 1% of heterology across of all samples collected during that time. So a lot of thanks to Kurt and the D-Lab, just outstanding work as always. Here's the mycoplasma data. Again, the dates in which positive samples were recovered, the times when they were found, the points, the distances from the source, the PCR, and the sequencing. And this is Simone. We used 232, Eileen's original challenge inoculum, which is very different than the isolates in the field. And so it was very easy to distinguish our isolate. And I apologize for this slide, but this is Simone's table she prepared for me, just showing that the inoculum as compared to all of the isolates. And there was 100%, or actually 99.99% homology between the mycoplasma isolates when compared to the inoculum. Basically, we found the samples at 2 different points, northwest and southeast. So here's the infected source. Southeast wind blowing. We found, you can see the mycoplasmas at 1 mile and the PRRS and mycoplasmas at 2 miles. So a southeast wind as well as a northwest wind. Again, infected source, northwest direction of wind flow, and southeast collection. Okay? Here are the weather data, and this is just numerical. No analysis has been conducted. But just to show you what it was like outside when these positive samples were recovered from our weather station. Here are the various parameters measuring barometric pressure, temperature, relative humidity, velocity, gust, high-speed winds, directionality, and then sunlight intensity is measured by watts per meter squared, or photosynthetic active radiation as an indirect measure of cloud cover or nighttime, and then precip. So here are the mean and the range of these various parameters that were collected during the time the positive air samples were recovered. So if you take this and divide by 34, you'll get our U.S. version of barometer. Basically, we had falling barometer during this time. Fairly cool days, high humidity, low winds as far as velocities, very directional, southeast to northwest, and then very low levels of sunlight. Our weather station, basically at nighttime, will record a 0.6 watts per meter squared and a 1.2 PAR, photons, per meter at that time. So these are the nighttime readings. You can see just from, these are very low numbers. In a very sunny day, these numbers are up in the thousands. And so these numbers are indicative of nighttime prior to the sun rising or very cloudy periods in which we were recovering these agents. And then a little bit of precipitation on some of these days too. And again, just numerically speaking, there seems to be some similarities between the days in which we were, the weather patterns on the days when we were collecting PRRS virus and mycoplasma. Either nighttime, cloudy, cool, moist, directional winds moving at slow speeds. So to conclude, from this project, airborne spread of both agents were documented out to 3.3 kilometers. The organisms recovered appeared to originate from our source population. Viable virus was present out to 3.3 kilometers. And certain meteorologic conditions may influence. We haven't analyzed it yet. But they may have an influence on long-distance airborne spread, such as directional winds, low sunlight, high humidity, cool temperatures, perhaps a low-pressure system type of an approach. That kind of a day. So did we answer our questions? Is MERV-16 air filtration effective against multiple pathogens? I think the answer is yes. Do cost-effective alternatives exist? I think yes. Further testing is needed, but so far so good. And can airborne spread of pathogens occur over long distances? Definitely. Last slide. What's a big picture in regards to significance for area and regional control and elimination? I think we all understand, a lot of you have known this for a long time, that aerosol transmission is a significant risk factor for area spread of PRRS virus. Long-distance airborne spread of PRRS virus and mycoplasma, I think, has now finally been demonstrated. Air filtration is an essential component of a PRRS virus biosecurity program for swine-dense regions. I don't think we can survive without it in swine-dense regions. And options are identified and testing is underway.